Hello, Ramesh.
Sir,
I'm audible.
good evening. Sir, we will
Yeah.
wait for 3 to 4 minutes. If somebody will join, then we will start.
Okay, okay. But
Yes.
already time is means like they can.
Started, yeah, I know. But I think only I am in this meeting. Nobody is in this meeting. So we can
It's
wait
no problem.
according to me
Yeah, no problem.
for a few minutes.
Okay. So one more attendee came.
Yeah, we can wait 1 to 2 minutes more.
Yeah, sure. So I just wanted to know that means are you going well with this assignment, Ramesh Chidambaram? How are you performing?
Which assignment? Current assignments, either overall. You are talking about overall assignments.
Overall assignment means how your performance.
Uh,
Means like
Actually,
yeah.
your assignment is beneficiary to solve the
No,
our
no. Means like
assignment.
yeah, it's okay. But I am asking about means are you able to get more than 70% marks or below than that?
Yes, sir. Out of 9 assignments, I got only 1 to 2 assignments 40 marks. Otherwise, all assignments I got around above 70%.
Yeah, that's very good.
Some
And
assignments I got
I think there is some rule that best of 8 assignment will count for the final assessment, right?
yeah, I think only 8 assignments will consider. 4 assignments will not consider.
Yeah, miss the best one, whatever you performed best, that will be counted.
Yes,
So
correct.
you just uh, approach each assignment and see means like in which assignment you means luckily some assignment you may get some less marks, but
Yes.
the best
May I
assignment
know,
will be
sir?
counted.
May I know about the final exam marks? How much marks will consider for the pass?
Means final exam I am not clear.
Yeah, that means the offline exam.
I'm not clear means they are if you have uh, gone through assignment current assignment and like gone through this subject, I think hopefully you will able to solve there also. Means most of this problems from the means assignment type only. Those who are able to solve the assignment problem, they will solve the problem. So I would suggest that first revise the assignment problem before go to exam. First revise the assignment problem, then see the lecture, means see the lecture notes and make short notes. But I
Yeah,
would suggest that give the first priority to your assignment. If you are well confident in assignment, then you will not face problem in exam also.
yeah. Now 1 month is remain to start the
Yeah,
exam.
Yeah, yes, Ramesh.
27 is the date of examination.
Yeah. So it's okay. Mohan is asking before asking question the corresponding can discuss resource material can we give him. So, yes, that's true, but some problems are just given to means like some problems are one two problems need to be little bit I think so, but we are not. It is done by all the organizers. So some problems we have to like a little bit tricky. It happens. So okay, all right. So let us begin the session.
Yes, sir, sure.
So hello everyone, I welcome you in this live tutorial session number 10. And in today's session, we are going to see this interface of PV with pump storage system, hydro pump system. And as usual, we will first revise the contents for this big 10, and then we will solve the we will solve the some typical problems based on this theory and concepts on this big 10. So if you see this water pumping system that is interface to this PV panel. So we have PV panel, and then as we know that this PV is a DC source. So we have to connect with DC-DC converter, and then there is DC motor, and this DC motor is connected to this uh, pump, and it drives the pump, and we can have uh, with the help of this pump we can store this water at a certain height, and we can uh, have this potential energy equivalent to this hydraulic power, hydraulic energy. So if you see in this system, then we are having some terms. There are some terms and terminology that we have to very aware, and we have to just that is very useful for solving the assignment. So first time in the suction head, HS, or it is also called as static lift. So suction head is this vertical distance between this sump and this pump, and center of this pump is that between the center of pump to this sump or this water beneath this uh, impeller. Now this SD denotes this delivery or discharge head, and this is also called as static head. And most of the water pumps used in our homes are usually of single phase induction motors, and these pumps in irrigation fields for agriculture purposes are generally are three phase induction motors. And for PV application, since output is DC, so DC motor will be a better choice for this water pumping application. So if you see the total vertical head, total vertical height, you can see this HS plus ST. But this is not, if you see in the real system, real application, the one term is also coming that is called equivalent head representing the friction. So that is represented by dynamic head, and this is the summation of suction head plus discharge head plus this head loss due to friction. And this head is direct measure of in fluid dynamics. This whatever this dynamic head is direct measure for the pressure. And these are some terms. Total head is this suction head plus delivery head, and dynamic head equal to suction head plus delivery head plus friction head. And HF, as I said, this accounts for pressure loss due to friction, and HF represents this equivalent head in pump due to fluid flow in the pipe, representing this friction in the pump due to fluid flow in the pipe. Now, if you want to write this potential energy, then we know we have undergrowth in this our 12th standard or 10th standard. So there mgh. So mg this force and g this height, and m this mass we represent as density into volume, and this mass density we represent is through rho, and density of butter is taken as 1000 kg per meter cube, and this q is discharge volume, and we take it is in meter cube to get the energy in joules. So if you substitute this mass in this energy in the energy expression, then you will get rho qgh. So this is the hydraulic energy, that energy required for lifting water from a lower level to higher level. Now if you substitute this value and write in terms of write in this terms of volume of water and this height. So this density of water 1000 kg per meter cube, and g and this gravitational acceleration is written as 9.81. So it will coming approximately equal as 10 to the power 4 UH in joules. Now if you see this, there are some conversions that are very useful. So we know this electrical unit. So electrical energy unit. So one unit will be represented as 1 kilowatt hour. So if you write in watt second or joules, then 1 kilowatt equal to 1000 watt, and 1 hour is equal to 3600 second. So it will equivalent equal to 3.6 into 10 to the power 6 watt second joules. So if you substitute this now if you as we have seen this potential energy in joules. Now if you want to write in kilowatt hour, then it will be divided by 3.6 10 to the power minus 10 to the power 6, then you will get in kilowatt hour. So it will be 2.725 into 10 to the minus 3 QH kilowatt hour, where this volume is in meter cube and H in meter. Now generally this we don't represent the volume of butter in meter cube, we take it in liter. So we have to consider this expression 1000 liters equal to 1 meter cube, and that is very important. So now if we substitute this 1000 liters equal to 1 meter cube, then how we get the equations? So here if you take this energy from this top one, then here this volume is independent in meter cube. So if divided by 1000, so that you can represent this volume in liter. So you will get 10 into Q into H, and where this volume of butter represented in liters. So these are some expressions. So here two terms are important, that 1 unit is equal to 1 kilowatt hour and 1000 liters equal to 1 meter cube. If you know this conversion, then you can convert in any form. Now how you write this hydraulic power? So this is the rate of energy. So hydraulic power is, you have to take the derivative of hydraulic energy. So hydraulic energy is rho q gh. So this rho gh are constant term. So if you have to take the volume inside, so it will be rho q dot gh watts. So this is the hydraulic power. Again you substitute this density of water and this gravitational acceleration constant 9.81, you will get these two expression. So first one is here this discharge rate given in. So here q dot is discharge rate, and q is discharge volume. So here q dot is discharge rate, and that is given in meter cube per second, and h is in meter. And if you write in liters per second, so you have to divide by 1000. So you will get 9.81 into q dot into h. So this finally we are having with this expression, where this discharge rate in liters per second and height is in meter, and where this dynamic head equal to this HS plus HD plus HF. Now this question comes that how we have to estimate H. So we know this suction head, we know this discharge head, and how we estimate this friction means this head loss due to friction. So let us see how we can estimate this HF, this head loss due to friction. So before that means whenever we are taking this total physical head, it is not always to that we just sum up this suction head plus discharge head. Because here first example, if you see here this, like we are having this sump that is below this centrifugal pump, and then we are having this tank. So if you see this height from the sump to this total physical head, then it will be counted as suction head plus this dynamic head. Now if you see this second setup, so here this sump is above this centrifugal pump. So now if you take the equivalent height, equivalent total physical head, then you will see that the distance from this sump to this tank is it HD minus HS. So it is the, you can just rightly say that it is equivalent distance in the sump to this water tank. So in the setup to the suction head of the source is such that it is above the pump central axis, means that is impeller, and thus there is positive pressure which aids the pump to the push water. So now coming to this estimation of head loss due to friction. So there is some empirical relationship, that is first one is Darcy-Weisbach formula, and that expression is HF equal to F into L upon D into U square upon 2G. Here this F is friction factor, L is length of pipe, and D is, here L length of pipe will be counted both this vertical and horizontal distance, and D is the inner diameter in meter, and U is the velocity of fluid in meter per second, and G the gravitational acceleration constant 9.8 meter per second square. So this is the empirical relationship, that this relationship, Darcy-Weisbach formula. And now how we know this friction factor? So friction factor depends upon the fluid flow, and we know that fluid flow are of two types, laminar flow and turbulent flow. So for the laminar flow, and this type of flow depends on the Reynolds number. So if Reynolds number is less than 2000, that we call as laminar flow, and if this Reynolds number is greater than 4000, that we call it as turbulent flow. For laminar flow, this friction factor is quite easier one. It is the ratio of 64 upon Reynolds number, and Reynolds number is Vx upon mu. So first you find the Reynolds number, and based on this type of flow, you find this friction factor. So if this Reynolds number is greater than 4000, so if Reynolds number is greater than 4000, it is turbulent flow. And for turbulent flow, finding the friction factor is not that much easy as like this laminar flow. So in this, if there is turbulent flow, then we have used to this Colebrook-White formula, and this expression for this Colebrook-White formula is this one, that is transcendental equation, and this is, if we find the solution, this is analytical solution cannot be find from this equation, so we have to use this iterative methods. So in this Colebrook-White formula, we have this roughness ratio, that is epsilon upon D, and this epsilon is If you this epsilon is the height of bumps on the inner wall of the surface of pipe. So epsilon is the height of bumps. So in pipes we have, like suppose this is pipe, so we are having this pipe means the surface is not purely, how you can say, means a smooth. There will some bumps, so we have to take the maximum height of the bump on the surface of pipe, and d the inner diameter of pipe. And here this height of bump on the inner surface pipe for material it is given for PVC pipe nowadays being used. So this one for PVC pipe, this is 0, and for asbestos cement it is 0.012. For a steel pipe it is 0.1. For a smooth concrete it is 0.4. So here this roughness ratio is more for a smooth concrete, and for PVC pipe that is nowadays very much used in our household and irrigation purposes many places. So it is this reference ratio is 0. So here I have written about this roughness ratio. The roughness ratio depends upon the smoothness or inner walls of the pipe through which H2 is flowing. And this roughness ratio is epsilon upon d, and where this epsilon is height of bumps on the inner walls of surface of the pipe, and d is the inner diameter. As I said, this if Reynolds number is less than 2000, then this is the flow is laminar, while this Reynolds number is greater than 4000, this water flow is turbulent. And between this, if Reynolds number you got between 2000 and 4000, then friction factor is not clearly defined. Means as we have seen this, there are two ways by which we can find the friction factor. Now suppose this Reynolds number comes in between 2000 and between 4000. So what we'll take, we will take this, we will go through all both the ways. Means like we consider the laminar flow and turbulent flow, and in both cases, whatever is the maximum value comes from both the method, we will take the maximum of them. So if the Reynolds number is 3000, we will find this through laminar way and turbulent way. Means we will apply this laminar method and this Colebrook-White formula, and the maximum of it we will take this friction factor. Earlier what was used means to find this friction factor, these Moody charts were used, and these are the graphical printers of Colebrook-White formula. So this is now Moody chart. Sir has already explained means how you can get this Moody charge from this Colebrook-White formula. So he has provided the octave code. From there you can get the Moody chart from this Colebrook-White formula. So this one is a Moody chart, and here if you see this Reynolds number and this friction factor, and this is the roughness ratio for different. So the friction factor versus Reynolds number for different toughness ratios. So this friction factor is less for this as this roughness ratio having lesser value, this friction factor is of lesser value for the same Reynolds number. As this toughness ratio increases, this friction factor also increases. And here if you see this transition means like for laminar flow. So this is the region for laminar flow that is denoted by blue one. So in this blue one region, we can see this the plot it is varying linearly, and beyond this 2000, and suppose this is 4000. So between this 2000 4000, we are having transition region. we having transition region for this fluid from laminar flow to turbulent flow. And in turbulent flow, we are having this type of plot. So, and for difference toughness of flow, these are plotted from this Cordebrook, from this, how I can say, Colebrook-White formula. So, Moody charge is the graphical representation of Colebrook-White formula. Now, how you can numerically solve this Colebrook-White formula? So, it is not a transformation equation. So, you have to go it to iterative approach. So, let us. So, this is this Colebrook-White formula. So, you have considered this 1 upon root f equal to x and a equal to roughness ratio upon 3.s. So this term is considered as a, and 2.51 upon Reynolds number root f, this number is considered as b. So you can write x equal to minus 2 log 10 a plus bx, and let us consider this gx, and let us consider this as function x plus 2 log 10 a plus bx. So this function, so you have to solve this GS equation iteratively such that Gx equal to 0 for the solution obtained value of the x. Now we will use this Newton-Cotes method to solve this function iteratively. So we are having this function, and let us take the partial derivative with respect to x. So we will get 1 plus 2b upon a plus bx. So this Newton's Cotes formula is g x cap equal to delta x del g upon del x upon xk. So this delta x is written as xk minus xk plus 1. So this is the iteration. So we will get the, we will first assume some initial value, and using this Newton's Cotes formula, we will iteratively solve this equation. Now you have to substitute the values for this gx and g dash x to solve this equation. So you will get the next term. So we substitute gxk equal to this one, x plus 2 log 10 a plus bx, and you have find this g dash, that is coming 1 plus 2b a plus bx. So you will get this one, and you upon simplifying, you will get this term xk plus 1. Now means you have to, as I said, this you have to consider this initial term, and this initial gates you have to take it from Moody chart, and finally after some iteration you will get same friction factor as some term that 1 upon x square plus 1 x square plus 1 whole square. So this is the summary of hydraulic power calculation. So if you face any doubt, anything you want to ask, you can interrupt me and you can ask your question. You can type your query in the chat box also. So this is very important, means how you calculate the hydraulic power. So what are the specification we need to they need to be mentioned. So these are the specification that will we have to know before finding the hydraulic power or hydraulic energy. So the specification are, you should know this discharge volume, how much water you want to lift in overhead tank in a day, and you also want to know your discharge time, means like in how minute time you want to fill your tank or fill your means whatever the tank you have. So you also need to your discharge time. Then you also know your the inner diameter of pipe through which this water is flowing, and through this water is pumped. And you also, then you can easily calculate this area, cross section of area pipe. So there is no need to know of this area because you can find from diameter. And you also need to know this total length of pipe, and this includes both vertical and horizontal. Means you don't think that only this vertical will count, horizontal we have to also consider, because this there is head loss due to friction. and the significant head will count due to friction. We will see in one of the example later. And this mu is kinetic viscosity. You also need to know. And this epsilon is height of surface bumps that present inside the pipe. And this hx is suction head and hd discharge head. You can measure these heads. So these can be measured. These can be measured. While HF you have to find it based on the data. So first, based on the data, first you will find the discharge rate. So this is the discharge rate. First you find the discharge rate, and then discharge rate is nothing but discharge volume upon discharge time. And then you will find the velocity of water. So E will be discharge rate upon area, and you can find the area from this uh, pipe specification. And from this kinetic viscosity and this velocity of water, you can get this Reynolds number. And after finding the Reynolds number, you have to find the friction factor, so such that we can estimate the head loss due to friction. So another term we need to know, that is HF, and that should be estimated or calculated. So upon knowing this roughness ratio, we will apply this based on this type of laminar type of the water flow. You will, if there is turbulent flow, then you will apply this Colebrook-White formula expression, and from there you will get the friction factor, and you will apply this friction factor in this expression. And what is this expression called? This expression is called as Darcy-Weisbach formula. Now we are having with all the head expression. So we will find the total dynamic head. So total dynamic head is the sum of the suction head, discharge head, and this head loss due to friction. Now we have to substitute this equivalent head in this hydraulic power calculation. So hydraulic power calculation, we know this 1000 into gravitational acceleration constant 9.81 into discharge rate into this height, equivalent height, or this dynamic head. And then we will find this hydraulic energy. So this hydraulic energy is this hydraulic energy that will come here. You have to take the volume of water irrespective of the discharge rate. And here you have to take the discharge volume in the while calculating the hydraulic energy. Now let us see the examples on this hydraulic power. So first, in the first case, we are having sump, and then we are having this centrifugal pump and this centrifugal pump. So this is type of household application, means like in one section we are having sump, and it is passing through from one corner to another corner of house. So we are having this horizontal pipe, and then this is discharge head, delivery head. So delivery head height is 20 feet, and we are having overhead tank. So this discharge volume is the size of overhead tank. So it is 1000 liter. So it is specified in the question that how much amount of water you want to fill the tank. Sometimes it is given 80%, 70%. So based on this, you have to take the discharge volume. If they have given in the problem that you have to consider 70% or 80% of the overhead tank, then you have to multiply with 0.7, 0.8. So it will be coming 800 liter or 700 liter like that. And this, you want to fill this overhead tank in 10 minutes, so you can find the discharge rate, and this inner diameter is given, and so 1 inch equal to 2.54 centimeters. So this is very important, you have to remember this. We have to convert in this standard SI units, so we have to convert in meter. and 1 inch is equal to 2.54 centimeter. So you converted into inner diameter of pipe in meter like this, and this suction head is given as 6 feet, and 1 feet is equal to 12 inch. So this is also important. 1 feet equal to 2 inch and 1 inch equal to 2.54 centimeter. So suction head, you can write, you can convert feet into meter like this. So as I said, this discharge volume is the volume to fill in day, and discharge time is time in which discharge volume is expected to be filled. Now coming to this total length of pipe. Total length of pipe is suction head, and then we are having this horizontal pipe length, and then with this discharge head. So this coming as 146 feet. So 140 you have convert into this meter, and then you will find the cross section area of pipe, and then you will find this water velocity. Then you will find this Reynolds number, and this Reynolds number is greater than 4000. Therefore, it is turbulent flow. And since this pipe is PVC, so this height of uh, height of bump on this inner pipe is 0. So this roughness factor is also 0. And since this is turbulent flow, so then we will use the Colebrook expression, Colebrook-White flow expression to estimate this friction factor, and we got this friction factor as 0.018683, and then we'll use this head loss due to friction from this Darcy-Weisbach formula. Now, then you can find this total dynamic head, this suction head plus discharge head plus head loss due to friction. And then we will find this hydraulic power. So it is coming 425 watt. So this much hydraulic power we needed to pump the water from the sump to overhead tank. Now what we do apart from means in the previous example we have not used the solar PV. Now in this example we will use the solar PV. So in this case of solar PV, it is based on the radiation. So let us we don't put constant on this delta T, that is discharge time. So apart from the we are taking discharge time as some 10 minutes or something, means very less time. Let us link it to this insulation at the place, means we are giving the discharge time more. So how much this hydraulic power is needed? So this is HAT minimum given for Bangalore, and let us take based on this standard insulation, this delta T is coming as 4 hours. So first we will find this discharge rate. So discharge rate is coming as it is very less because delta T increase. Since delta T increase, so discharge rate will reduce. So it is 0.07 into 10 to the power meter cube per second. So in solar PV, what we used to do, we used to increase the overhead tank size because we have uh, increased the discharge rate because based on this atmospheric effects, it means based on the irradiation. So we have to increase our overhead tank so that we have the capacity to discharge in more time. So just like previous case, we will get this head loss due to friction from the Darcy-Weisbach expression, and then we have this dynamic head. We are getting a 8 meter. So we increase this, as we increase this, as we increase this discharge time, we are having this head loss due to friction also reduce, and this total dynamic head, most of the count is suction head and discharge head. So this is also reduced. Therefore, this hydraulic power will also comes down. So this power is much less than 425 watt. Open example 1, and here this discharge rate is reduced to a greater extent because discharge time is spread through the whole day. Now let us see the third case, that is borewell system. So in the borewell system, there is no suction head because this motor and uh, motor and pump both are at present at the same height. So both are present at the same height. So suction head is 0, and this Q, this discharge volume is 100 liters, and we have put delta T in in half minute, that is 30 seconds. So it is very less. So let us find this inner diameter of pipe. Inner diameter is given a 4 inch. So we know this how to convert inch into meter, and we will find the discharge rate, and then we will find the equivalent head or this water velocity. So H is equal to 0, and this discharge head is given as 600 feet. So you convert into meter, and then you will find this water velocity, that is q dot upon a. So you will get 0.41 meter per second. So then you can find the Reynolds number to find this head loss due to friction. So Reynolds number is ud upon mu, and mu is given in the given in the problem. So it will coming as 41,656. So it is turbulent flow, and this height of bump in the pipe is given as 0.1 mm for a steel. So we have taken the steel pipe here. So roughness factor we got 0.001, and once the roughness factor known, and since this is turbulent flow, then we will apply this Colebrook-White formula. So we will get this friction factor, and upon knowing this friction factor, we will apply this expression H to get this head loss due to friction. So this one is empirical relationship, and this is Darcy-Wesch. And now we'll find the total dynamic head, that is sum of all the heads. So it is suction head plus discharge head plus head loss due to friction. So it is giving us 183.4 meter. Now we'll find this hydraulic power. It is coming as 5.99 kilowatt. So you can use, for this application, you can use 7.5 or 10 HP motor, because you have to use more than the hydraulic power that needed. So you can take the motor as accordingly. Now coming to the type of pumps. So there are two pumps have been covered in this course. One is centrifugal pump, and another one is reciprocating pump. So this centrifugal pump, so it comes under the class of dynamic pumps, and this operation is based on centrifugal force. So and this pump is rotating at high speed and creates pressure difference. This pressure difference created due to high head rotation sucks in H2, and it routes the H2 towards center. So we will see one video based on this centrifugal pump and reciprocating pump. And because of the centrifugal pulse, water is pushed out in the outlet and creating pressure difference, and process continues. Therefore, this higher the speed of water, larger the pressure difference, and more the discharge. And this is the head versus this discharge rate graph. So here this, and if you see this load, as this speed increases, this discharge head and discharge rate graph also proceed towards this one. And below this threshold speed, everything goes into friction loss only. Uh, there will no discharge of water through the pump. And here this point ABC are called this base efficiency point, and how it is coming. So since this, we know this hydraulic power is rho q of dot gh, and along x-axis we are having this head equal to 0. So this pH equal to 0, hydraulic power is equal to 0, and along y-axis this q dot equal to 0. So since both expression are coming in hydraulic power, then both x-axis and y-axis, we are getting hydraulic power equal to 0. So in between them, we having this hydraulic power is maximum. And at these operating points, efficiency is also maximum, since this in between them, this hydraulic power is maximum, so efficiency will also maximum. And we recommended to operate this centrifugal pump at this best efficiency point. So these are the specification for this centrifugal pump. So the suction head need to be less than 10 meter, and this priming is needed. And what is priming? Priming is you have to fill up the centrifugal pump with water first, then switch on the motor. It is not advised to just before filling up the water, you switch on the motor. And then we are having the shaft torque. Shaft torque is coming at proportional to omega square, and head is dependent on flow rate and speed. And a speed below threshold speed, no water is pumped. Now coming to the stage, means coming to this stage of this uh, pump connection. So here this one is single stage, and in single stage there are two types of admission, that is single admission and butter admission, and double admission. In single admission, only from one side only this water is coming inside, and from double admission, this suction of water is doing through these two inputs. So if you compare the single admission with double admission, then there are some advantage of double admission over single admission. Means water emitted from both parts will balance the impeller wheel, and this reduce impact on the bearing. And this delta P, that is P1 minus P2, it forces water out of the impeller. And if you see this multi-stage, that you have cascaded the pumps. So in multi-stage also there will be single admission and double admission. And this multi-stage is used for deep wells, or in case of submersible pumps where you have to pump to a greater head, multi-stage impellers are normally in the pump. And in multi-stage, delta P gets added from one stage to next. Because of the addition of pressure, there is sufficient differential pressure from first to last stage, which helps in pumping water to greater heights. So this is the benefit of this multi-stage, and generally be used for deep wells or in case of submersible pumps. Now let us see this interfacing PV to pumps. So we are having this PV, and then we are have this chopper. So since there is inherent armature inductance present inside this DC motor, so there is no need for this LC filter connected externally. And that and this is motor that is connected at the output of chopper. So if you see the expression of developed torque, so developed torque is equivalent to the summation of inertia torque, bearing torque, and load torque. So how you can write the voltage across this inductor? So voltage across the inductor will be Vt minus Ia Ra, and this one is back EMF. And we know this back EMF is proportional to this angular velocity, so it will be can written as k omega. So this expression got across this uh, armature inductance. Since this motor is rotating with mechanical time constants, there is inertia, and this omega will not vary as quickly as electrical parameter I. And we have considered this Ra is very small, so we can write this voltage across inductor that is Vt minus k omega. And for period Ts, Vt and Ev are fairly constant. And since during this turn on time, VL is constant and positive. So this Ia will be having rising slope, and it is Vt minus Ev equal to 0. So it is dTs. So I having rising slope, and it will coming a Vt minus Ev upon LA, and for when switch is off, this slope will come as minus V upon LA. And this duty cycle be used for controlling the armature current. And this developed torque is directly proportional to armature current. So we can say that this duty cycle is used to control this armature current, and this armature current controls this developed torque, and this developed torque controls omega, and this omega controls pressure difference in pumps, and that in that way this flow rate is controlled. Now coming to this reciprocating pump. So reciprocating pump is used for having lesser rating. So here if you see this crankshaft and wheel, so if this one is at one position, so if this is at one pressure, this piston will be at this point, so it is pushing up the water to deliver the water. And when this position is at 2, then this piston will be at the 2 position, and there will be pressure difference, so it will suck the water inside. So when this piston is at one position, it is delivering the water, and when the piston is at 2 position, it is sucking the water. And wheel is this crankshaft is connected to this motor. So whatever means greater the speed, greater will be the to and fro motion, and greater will be the water delivery from this reciprocating pump. And how will you find the discharge rate for reciprocating pump? So here are some terms. First is a stroke length. So this is the distance. This is the difference. This is the distance between this first position and second position. So this is a stroke length. And an inlet and outlet valves are unidirectional. Means water will come from the inlet side and water will go from the outlet side. And any the number of strokes per second. So means how many times this coming means going from 1 to 2, that is the denoted number of strokes per second. And omega is the speed of wheel or crankshaft. And A is the area of this cylinder, and this in then you can write this discharge rate at A into S into N. And area you can write pi by 4 upon d square into S into omega, as N is directly proportional to omega. So number of strokes per second is directly proportional to omega. So you can write this Q dot is directly proportional to omega. So this is very important. This expression comes in reciprocating pump that is not depending upon the load. Earlier, this discharge rate is depending upon the load, but in this case, this discharge rate is not depending upon the load. So, and since this in first equation, this one in the first equation, this D and S are constant, so we can say that this discharge rate is directly proportional to omega, that is independent of head. In earlier case, this discharge rate is depending upon the head. So normally crank wheel rotates at lower speed and motor speed is high, therefore we required gearbox. So this crankshaft is having not that much speed, and while this motor speed generally be higher speed, so we require gearbox in this if we are using the reciprocating pump. And since the gearbox are expensive, so reciprocating pumps are not used in the lower power and less efficient pumping application. In this application, centrifugal pumps have advantage over reciprocating pumps. And this is the water pumping system. So we have a PV panel and power converter, motor, then pump, and then hydraulic system. So how much PV power be required for this to pump to deliver that much of hydraulic power? So based upon the efficiency of these interfaces, power converter, motor, pump, So it is coming approximately 2 times of the hydraulic power. So this is the size of PV for this PV requirement for HRT minimum condition of the annual insulation. And there are some pumped hydro application. So I would say that you go through it. So this one is water pumping. So it is same means here this same motor is used a generator and same pump is used a turbine. While in this decoupled system, we are having motor different and generator different. So this advantage decoupled system is water can be pumped up at lower power and spread across the whole day. And this hydraulic power needed to be low, and this electrical output during night time can be high power output in AC or in DC form. But disadvantage that you need to install two system. That's why it is having additional cost. And these are some of the uh, representation for this hydropower expression. I would suggest to go through these slides, and because we have less time, let us come to solving the problem. But before that, I have put two videos so that you can see it and differentiate between the reciprocating pump and this centrifugal pump. So this first one is reciprocating pump. So can anyone means verify that you are able to listen the video? Means when I am running it, are you able to listen the video?
Yeah, it's visible
Okay.
and it's running.
So I will just keep it here. You can go through this. So you can see this reciprocating pump. So this is about this centrifugal pump and reciprocating pump. This have nice visualization. So now let us come to solve the problem. So let us see the first problem. So the first problem is that it is quite easier one. 1000 liter of water is stored in an overhead tank at a height of 10 meter. What is the stored energy of that overhead tank in kilojoule? And take this gravitational acceleration constant at 9.8 meter per second square. And the options are shown over here. So just I would request you all to solve parallelly with me. And if you are getting the answer, you can tell your answer and you can type your answer in chat box. Okay, you are not able to listen the sound. No problem, you can find many types of video, but you can, I think, hope you will see the visualization how these are working. This reciprocating pump and centrifugal pump. So let us solve this problem number 1. So first we will write the what are the things given and what they are asking. So the given is discharge volume. So discharge volume is given as 1000 liter. So whenever the liter they are given liter, first you need to convert in meter cube. So 10,000 liter. So we convert it to meter cube. So we know that we have to divide by 1000. So it will be 10 meter cube. And now height is given. Means here there is no height, no other different types of height. So it is single, you can tell it as dynamic height. So it is given as 10 meter. And what is the store energy of the that overhead tank?
Q
So
is
we know
1000 liter.
yeah, what?
Q is 1000 liter given.
Okay, it is mistake. It is 10,000. It is 10,000, not 1,000. So you can find the store energy, that is potential energy. So potential energy will come as mgh. So you can write m equal to rho qgh. Rho is 1000 kg per meter cube. Then q is 10 meter cube. Ge 9.81 meter per second square. And then h is 10 meter. So you will get 980 into 10 to the power 3 joule. The answer is 980 kilojoule. So the correct answer is B, 980 kilojoule. Yes, RK. If you have taken Q as 1000 liter, then it is correct. Rajnikant, you are also correct. Very good. Now let us see the next problem. So the second problem is that which of the following Reynolds number is a perfect range for turbulent liquid flow? So we have discussed it in the class and we have revised today also. So I want you all to give the answer. Yes, it is D. RK, you are true. That is D. So it is, when Reynolds number is more than 4000 water turbulent liquid flow. So D is the correct answer. And when this Reynolds number is less than 2000, then it is laminar flow. And when this Reynolds number is more than 4000, it is turbulent flow. So let us see the next problem. What is the roughness factor for a steel pipe with 0.8 inch diameter? This is also quite simple problem. So you have to find the roughness factor for a steel pipe with 0.8 inch diameter. So you need to know how to convert in inch into meter or millimeter. So we know the roughness factor expression. Roughness factor expression is ln upon d, and where if ln is the height of bump inside the pipe. So this is a steel pipe. So steel pipe having its ln is 0.1 mm. So 0.1 mm is the ln. We have to find the d. So how we'll find the d? So ln of a steel pipe is 0.1 mm, and diameter of pipe is 0.8 inch. So converting inch into millimeter, so you have to multiply with 25.4 mm. So put here 0.8 into 25.4 mm. So you will get 4.92 into 10 to the power minus 3. So it is 0.00492, approximately equal to 0.005. So correct answer is B. Yes, RK, you are correct. Correct answer is Rajnikant, you are correct. Very good. So those who are solving problem here, that is very nice. Don't leave it. You will do in later. You will do, because just it will be it will become late. Now let us see the next problem. So it is linked with the no, it is new problem. It is expected to send 10,000 liter water to a 50-meter top storage system in 20 minutes. The diameter of a steel pipe is 1.5 inch. What is the Reynolds number for this water flow? Take kinetic viscosity of air. Kinetic viscosity of water is 0.6531 into 10 to the power minus 6 meters square per second at 40 degrees. So you have to find the Reynolds number, and for Reynolds number, you have to find the water velocity, and for water velocity, you have to find the discharge volume. So let us first write the what are the things given here. So we are giving with discharge volume. Discharge volume is given in per 1000 liter, and height is given as 50-meter storage system, and then delta T, discharge time is given as 20 minutes, and then diameter of a steel pipe is given as 1.5 inch, Diameter of pipe become 1.5 inch. So let us convert it right now only to meter. So 1.5 inch into millimeter will be 25.5, 25.4 millimeter. Then you have to divide by 1000 to get in meter. So you will get 0.0381 meter. So this kinematic viscosity of air is also given. So this is 0.65, 0.6531 into 10 to the power minus 6 meter square per second at the rate 40 degrees Celsius. You have to find the Reynolds number. You have to find the Reynolds number. So first we need to know the Reynolds number expression, that is mu d upon mu, ud upon mu. So this is the Reynolds number expression. So we know d and mu, but we don't know the u. So before that u equal to what? So before that we will find the u. So u will be q dot in upon a. So we don't know q dot. So we will first find the q dot. So q dot is discharge rate is q upon delta t, discharge volume upon discharge time. Therefore, this discharge rate will be 10,000 liter. So 10,000 liter, you can write it in meter cube. So it will be 10 meter cube. So it is 10 meter cube. And then 20 minutes, you can write in second. So it is 1200 second. So it is 1200 second. So it is 8.33 into 10 to the power minus 3 meter cube per second. Now we can find u. So u equal to delta discharge rate upon area. So it is 8.33 into 10 to the power minus 3 meter cube per second. Important thing is that you have to take care of unit always here, means while solving the problem. And area is pi by 4 into d square. So area is pi by 4 into d square, and d square is given as pi by 4 into 0.0381 square. 0.0381 square. So you will get it as 7.309 meter per second. So approximately you can take it as 7.31 meter per second. Now finally we can find the Reynolds number. Reynolds number is ud upon mu. So u is 7.31 meter per second. Inner diameter is 0.0381 meter, and kinematic viscosity of air is 0.6531 into 10 to the power minus 6 meter square per second. So you will get 42 4 lakh 26,406.88. So you can directly write in integer. So 4 lakh 26,406 is the answer. They have provided answer in the range, and the range they have provided for this problem, and the range they have provided for this problem is 4,10,000 to 4,30,000. Yes, 4,26,406. Very good, Rajnikant. So let us see the next problem. What is the total dynamic head of system in meter if the friction factor for the flow is 0.0135 in question 4? So they have provided the friction factor. You have to find the total dynamic head. Total dynamic head. Then so let us show. So here in this problem, they have provided the friction factor 0.0135 meter, and acceleration constant they have told you to use 9.8 meter per second square, and you have to use this Darcy base wedge formula, and this Darcy wedge formula, this friction head equal to F into L upon D, F equal to L upon D into U square upon 2G. So what are things given here? So for using this Darcy wedge formula, we have to we have to use this length of pipe L. So it is at 50 meter height. So length of pipe will be 50 meter. Inner diameter of pipe we have found it is 0.0381 meter, and then mu water velocity it is 7.31 meter per second. Therefore, HF will be 0.0135 into 50 upon 0.0381 into 7.31 whole square upon 2 into 9.8. So the head loss due to friction, it will be coming as 48.3 meter. Therefore, total dynamic head, that is height of the overhead tank is 50 plus HF. You can also write this height of overhead tank as HD. So 50 plus HF is 48.3. So you can see this friction head is not that much less. It is quite equal to the pipe length. So this one is coming as 98.3 meter. And they have provided the range for this problem, this NPTEL 95 to 101. I think no one got the answer. So let us, if you have any doubt, you can interrupt me. No problem. What is the hydraulic power required for water flow in question 4? So we have found the total dynamic head. Now it becomes so easy. Means we have found this total dynamic head H, and we know that hydraulic power is nothing but rho G Q dot H. So hydraulic power we know Hydraulic power we know rho q dot gh. So this simple expression we have to use, and it has used many times. So we have to remember this expression. Rho is 1000 kg per meter cube. We have found q dot is 8 point discharge rate 8.33 into 10 to the power minus 3 meter square per second, meter cube per second, and then g is 9.8 meter per second square, and then dynamic head is 98.3 meter. So we will get discharge and hydraulic power as 8204.62 watt. So they are asking in kilowatt. So it is 8.024 kilowatt. So this is the answer. And the range they provided for this problem, is 7.7 to 8.3. Generally, whatever the answer you are getting is why choosing the most without any approximation. Whatever the answer you're getting, they will provide the average, means some tolerance. Means if you take the average 7.7 to 8.3, it will come at 8 kilowatt. So and that's in that way they provide the range for the answer for the answer for the range for the any problem answer. Now next problem, what is the maximum flow rate in meter per second meter per second allowed flowing following the data of question 4 in if laminar flow data expected at the storage system. So you have to, since you got this turbulent flow, but they are asking you to take the laminar flow. You got the Reynolds number as 4,26,406, but they have asked you to take it as laminar flow and then solve the problem. So it is quite simple. That is not that much complicated. So they are asking that U max equal to what, so that we will get the laminar flow. To get the laminar flow. And this laminar flow condition is that you have to Reynolds number less than 2000. This is the condition for laminar flow. This is the condition for laminar flow. So we know that Reynolds number expression is UD upon mu. So this for laminar flow, so you can write U as Reynolds number viscosity upon D. So you can get the U max as R max upon kinematic viscosity upon D. So this expression you have to use for laminar flow. So you have to put R max as Reynolds number maximum 2000. Kinematic viscosity they have provided earlier in the question, that is 0.6531 into 10 to the power minus 6 meter square per second, and D is 0.0381. So you will get answer as 0.03428 meter per second. So the correct answer, it is approximately equal to 0.0343. So A is the correct answer. Will there be a topic on P panel mounting a structure selection of metal frame that can withstand 120 km per hour of wind speed, wind low, snow load? I think this topic sir has not covered, and I think we have to investigate which Rajnikant, you are correct. Miss, what are you asking about, Mohan? Formula is required. Okay, for mounting structure design. I think sir has not covered this type of topic. But yes, they we can look into the some research paper or some books. I am also not aware of this formula. So I am not. I think I have not gone through this type of formula. So let us see the next problem. So in this problem, a 400 volt DC motor is connected to pump water to an overhead storage tank. The hydraulic power required by system is 5 kilowatt. If the pump and motor system is 60% efficient, what is the rated current of the DC motor in ampere? So a motor is connected to the pump and that is providing hydraulic power of 5 kilowatt. If the pump and motor system is 60% efficient, so this efficiency is 0.6. What is the rated armature current of the DC motor? So let us take, we are providing the input power, and this motor is 400 volt rated. The hydraulic power they have provided this as 5 kilowatt. And they are asking about the armature current of the motor. Since efficiency is given, so therefore we can find the input power, that is hydraulic power upon efficiency. So it is 5 upon 0.6. So we will get 8.33 kilowatt. And input power you can write voltage into armature current. So this is 8.33 into 10 to the power 3. Voltage is 400 volt. Armature current you have to find. So armature current you will get 125.6 ampere. So you will get 20.83 ampere as the correct answer. So correct answer is 20.825. Let us see the next problem. In problem 8, if the efficiency of the converter system is, if the efficiency of the converter system is 90%, what is the required power rating of the PV panel in kilowatt? So it is asking what of, so here we are having the PV panel first, and then it is connected to chopper or some converter, and is connected to motor, and then it is connected to pump, and this is providing the hydraulic power of 5 kilowatt. So till here we have calculated in the previous problem. So here we are getting efficiency as 0.6 and input power as 8.33 kilowatt. It is asking that converter efficiency is. Anyone has doubt? 0.9. So what is the power rating of PV panel? So it is hydraulic power upon all the efficiency 0.9 to 0.6. So 5 upon 0.6 into 0.9. So it is 9.259 kilowatt. So it is approximately equal to 9.26 kilowatt. And the range the NPTEL has provided for this problem 9 to 9.5. If you see the PV panel rating, then it approximately equal to double of the hydraulic power, as we have seen in the lecture. So hydraulic power is 5 kilowatt. You are getting the PV power rating as 9.26 kilowatt. So it is approximately double to the hydraulic power. Let us see the next problem. The diagram below is for a single stage single admission centrifugal pump, multi-stage single admission centrifugal pump, single stage multi-admission centrifugal pump, multi-stage multi-admission centrifugal pump. Please all of you write your answer chat box. The diagram, this one is for which type? I got one answer, Rajnikant. Other one? RK, you are incorrect. Rajnikant, you are correct. Vikas, you are correct. RK, you are correct. So you are starting with incorrect. Mohan, you are incorrect. So since this is cascaded one, pumps are cascaded, so it is multi-stage. So the first thing is confirmed that it is multi-stage. So it is multi-stage because they are cascaded. And now for single or double admission, you have to say the number of admission. So since there is only one inlet, so there is single admission. If there are two inlets, then it is double admission, multi-addition. So it is multi-stage single admission centrifugal pump. So B is the correct answer. Now let us see the next problem. So a water tank of 100 liter capacity is located at a height of 10 meter. Calculate the energy storage in the water tank at 80% of tank capacity in joules. So here, if you see this, the tank capacity is 1,000 liter, but they want to fill the tank 80% only. So accordingly, you have to calculate the energy stored. So here, given water tank capacity is 1,000 liter. And if you write in meter cube, so it is 1,000 upon 1,000, it will be 1 meter cube. And height is 10 meter. Therefore, potential energy stored will be mgh, that we know rho qgh. So it is 1,000 kg per meter cube. Q is 1 meter cube, G is 9.81 meter per second square, and H is 10 meter. So you will get 98,100 joule. Is this correct or incorrect? Can anyone tell? Whatever the answer we got, it is correct or incorrect? Yes, it is incorrect. So we have to multiply with 0.8. So it is incorrect. So we have to take the 100% of, not you can that incorrect, 50% of tank capacity. You can at a starting take this discharge volume as 0.8 into 5 liter. You can also at the end. So E 0.8. So it is 78,480 joule is the answer. And the range the NPTEL has given for this problem is 78,400 to 78,600. Now let us see the next problem. In this problem, the water is discharged through PVC pipe as 10 liter per second. So it is, you convert into meter cube per second. So it will be 0.001 meter cube per second. You have to find the hydraulic power. Hydraulic power at a generator under the ideal conditions. So hydraulic power, we know that rho q dot gh. So it is 1,000 kg per meter cube into 0.01 meter cube per second. G is 9.81 meter per second square. H is 10 meter. So we will get 981 watt as the answer. And the range NPTEL has provided for this problem as 975 to 986. So let us see the next problem. Consider the battery. Oh God. I think it is. So I have to remove this. This one is the problem, 13 problem. So a PV panel supplies power coupled to hydrogen turbine set to a step down chopper. The chopper is operated at MPPT. The armature resistance inductance given. The PV terminal measure 220 volt, and then PV power is 1520 watt. Maximum power pressure. Chopper is operated 60% duty ratio. The DC generator used as a motor transfer electrical energy to potential energy. Calculate the induced EMF in volts. So this is lengthy, quite given lengthy one, but it is not not that much difficult. So let us take this ink. So first writing down the what are the parameters they have provided. Armature resistance they have provided 0.6 ohm. This armature inductance they have provided 1 millihenry. This PV voltage they have provided 220 volt, and this PV power they have provided 1520 watt, and then duty ratio is given as 0.6, and they have asked you to find the induced EMF, that is back EMF. So they have asked you to find the induced EMF in the volts. So let us make first the diagram. So let us take this as PV panel, and this is connected to chopper. So a step down chopper, and then it is connected to this motor, DC motor. This is RA, LA, and this is EB. So this is armature voltage, and this is PV voltage is 220 volt, and this is the PV current. So step and PV power they are providing. So PV power they are providing is 1520 watt, and this duty ratio of chopper is given as 0.6. If duty ratio is given, we can directly find this armature voltage D into 220, D into VPV. So duty cycle is 0.6, 220. So it is equal to 132 volt. Now, if you got this 120, 132 volt, then we can find this armature current also. How we can find the armature current? This PBV equal to VA into IA, because input power equal to output power. PV power is given as 1520 watt. So VA is given as 132 volt. So armature current will come as 1520 upon 132. So it is equal to 11.5151 ampere. Approximately you can take it as 11.51 ampere. Now you know the armature current, then you can find the induced EMF in volts. So this apply KVL. So it is VA equal to IA plus EB. So VA is 132 volt, IA is 11.51, RA is given as 0.6 ohm plus induced EMF. So you will get EV. So you will get EV as 132 minus 6.9, 125.1 volt. So the range they have provided for this answer. So for this bike EMF, we have calculated 120 to 130. We got answer as 125.1 volt. Now let us see the next problem. The capacitor bank is connected to the terminals of a standalone of induction generator. The reason is to supply the magnetizing current to IG. Why it is so? The induction generator does not have a separate field winding like a synchronous generator, and hence needs an external source to supply the magnetizing current. Therefore, the capacitor bank provides necessary active power to maintain the magnetic field required for the operation. So the correct answer is that this capacitor connected to terminals of standalone induction generator to supply the magnetizing current to induction generator. Because this IG does not have a separate field winding like a synchronous generator, and this needs an external source to supply the magnetizing current, and this comes from the capacitor bank. Now let us see the next problem. A ballast load is used along with a standalone induction generator for a startup, for better flux control, for maintaining constant frequency respective of load, for maintaining frequency inversely proportional to load. And the correct answer for this problem is C, for maintaining constant frequency irrespective of load. Because in a standalone system, the speed of the generator and hence the frequency can fluctuate with varying loads, and this ballast load is used to divert surplus power, ensuring that the generator operates at a constant speed, which helps to maintain a stable frequency regardless of the load variation. Now let us, so the correct answer is that for maintaining constant frequency respective of load, this ballast load is used along with the standalone induction generator. Now coming to the next problem. As the intensity applied incident on PV cell increases, the IV characteristic of cell moves. The IV characteristic of cell moves upwards. We know all about this. Now coming to the next problem, and this problem is quite with lengthy. So let us see this problem. A centrifugal pump is required to pump a water of 4 kilometers away from the location of pump through a pipe diameter of 0.2 meter having Darcy friction point of 0.0001. The average speed of the water in the pipe is 2 meters per second. If it is maintained constant of 5 meter tank, neglecting other losses, you have to find the absolute discharge pressure at the pump exit. You have to consider the atmospheric pressure acting on the water for calculating suction head. So let us first write the things they have provided. So length of pipe, they have provided as 4 kilometer, 4,000 meter. And then this diameter is given as 0.2 meter. Friction factor they have given as 0.01. The average speed in the pipe is 2 meter per second. Absolute discharge pressure at the exit. So based on this friction factor, we will first find this friction loss due to discharge, this friction head. means head loss due to friction. So we will apply this Darcy-Weis formula. So this is HF equal to F into L upon D into U square upon 2G. So it is 0.01, L is 4000 meter and D is 0.2, U is 2 meter per second square, 2 into 9.81. So you will get 400 upon, sorry, 400 upon 9.81. So you will get 40.7747 meter. So total dynamic head this constant head is given as 5 meters, so you have to add with 5. So 5 plus 40.7747, so it will be 45.7747 meter. So we have find the total dynamic head. Now we have to find the pressure. So pressure, we know that it is energy per unit volume. So the energy is EH upon Q, and we know that hydraulic energy is rho Q GH upon Q. So it is rho GH. Therefore, this pressure will come as 1000 kg per meter cube into G is 9.81 meter per second square. To dynamic head it will be 45.7742 meter. It will be 449050 Pascal. So this much is Pascal. So you have to convert Pascal into bar. So we know that 1 Pascal equal to 10 to the power 5 bar. Therefore, this pressure will be 4.49050 bar. Now, whatever the answer we got, this is not the absolute pressure, because there is some atmospheric pressure also. This pressure is the pump pressure. So this pressure exists at the pump. So the total pressure at the pump exit. So the total absolute pressure will be, you can write the total absolute pressure is the sum of pump exit pressure calculated and the total atmospheric pressure. And atmospheric pressure equal to 1 atmospheric pressure equal to how much bar? It is 1.013 bar. Therefore, we can write P absolute equal to P pump exit pressure plus atmospheric pressure. So P pump is 4.49 plus atmospheric pressure is 1.013 bar. Therefore, you will get 5.503 bar as the answer. So this is the answer for second last problem. So the correct answer for this problem is B. B is the correct answer, 5.503 bar. Now let us see the last problem. And this problem is also very easy, not that much complex. You need to know this continuity equation. If you know the continuity equation, then you can easily solve the problem. So here you need to know the continuity equation. And the continuity equation for an incompressible fluid state, for an incompressible fluid, this flow rate remains constant. This flow rate remains constant. Now we will apply this flow rate here. Therefore, flow rate at the cylinder equal to flow rate at the delivery pipe. Flow rate at the cylinder will be area into volume. Area of cylinder is A and volume cylinder is V. And for the delivery pipe, area of the pipe is a small a and delivery pipe is small v. So this is the first equation we got from the continuity equation. Now this horizontal means horizontal displacement of piston. You can write horizontal displacement of piston equal to x equal to r cos theta. So taking derivatives, take dx upon dt. So it will be v, and then we will take derivative of r cos omega t upon dt. So this will provide you v equal to minus r omega sin omega t. So we will take the magnitude only. So taking magnitude of this displacement derivatives. So taking magnitude only. So it will be v equal to r omega sin omega t. So this is the second equation. Now we will put second into first. Putting 2 into 1. So we will get, we have to find the velocity of water in the delivery pipe. And velocity of water in the delivery pipe is a small v. So the velocity of water in delivery pipe is small v. So we will write a small v in terms. So A into capital V upon A. So A, capital A upon a small a, and this capital V we got R omega sin omega t. R omega sin omega t. So the correct answer is, this is the velocity of water in delivery pipe. AY small a R omega sin omega t. So it is matching with the option B. So it is a small r. So that's all for today's session. Now we will close this today's session. Anyone having doubt, please feel free to ask me. रमेश, मोहन चिदम्बरम, आर के, रजनीकांत, विकास मिश्रा. Yes, Mohan, this will be little bit, how you can say, yes, if one question will wrong, this another subsequent question will go wrong. BR means BR PMRFTA, so we are only taking the tutorials. Yes, those who have, those who are solving, the student will not fail. If you are solving assignment and if you have gone through lecture, you will not fail. That I am 100% sure. You will, I think you will get Elite plus a gold certificate. At least those who are attending the session, those who are doing their work honestly, at least they will get a silver certificate. There will not means all that questions were cascaded. Some problems will be cascaded, but means if the option is given in the problem and in the first question you did incorrectly, then you, in second question you got wrong answer, then option is not matching, then you can assume that first option I have found some incorrect. So some way you have to put your mind, but I'm not sure they will ask cascaded question or not. I think you can means, since these are asking assignment, also they will ask in the uh, they will ask in the exam also. Means mostly means earlier during my student time, we means whenever I am writing this NPTEL exam, at that time they will ask the similar type of NPTEL problem. But I am not setting the question, so I am not telling anything confirmed. Okay, thank you all for attending session and good night to all.